Okay, so we'll do a little presentation about a project that, well, Robin has been working on, but I helped a bit. So it's Grout. It's a kind of new project that we worked on. So yeah, first of all, so who are we? We are two people from France working for Red Hat. So my name is Marchand. I'm working on DPDK as a maintainer, but in Red Hat I'm working on fast data. Okay, back? Yeah. So fast data path, which is actually OVS DPDK, which is used in Red Hat products like OpenStack and maybe OpenShift too. And so Robin Jarry, which is French
Bonjour.
too, who is French too, who is working on the OpenStack part, so for NAV use cases, which mean for telcos, basically. And he's been working on the end-to-end testing integration of DPDK for those customers. So, our presentation. So, why Grout? What is it? So, it's a graph router. We'll explain a bit why we wanted a new piece of software again, and how we visualize, well, how we envision this new project. There will be a little demo, some performance, but nothing really great to expect, and what we are working on. So why a new product? Well, no, product, a new project. So first of all, so we are working at Red Hat. We have some OpenStack software that is used by customers for telcos. They have their CNF, and usually they want to have an idea of what is getting better with a new version. So they want to do some non-regression tests. They want to have some ideas of how a VNF would behave on a platform. So they ask quite frequently about what can I compare, how can I compare my system with a reference network function. Internally, there is also an ask in Red Hat to do some non-regression tests, which is because we do change stuff in OpenStack every once in a while, so we want you to have a reference software. So far, well, we use TestPMD a lot. But well, TestPMD is only working at layer 2. It's not a router. And often, telcos are using IP forwarding or some similar functions. And so TestPMD is not really simulating the same stuff. There was also no way to simulate power consumption or to adjust power consumption in TestPMD. And so we wanted maybe to have something that is better in a new project. Also, there were some questions last year about how to get DPDK more visible, because we are providing DPDK, well, user space drivers, but it's not a software stack. And so, well, we wanted to maybe have something more usable for people, let's say a new software stack maybe, on top of DPDK. And so starting from this, we started to think about what was required for this new project. First of all, we wanted something independent. There are some VNF around, but they are usually written by some vendors. And usually it's not neutral. It's trying to use some hardware capabilities, or it's only supporting some NICs. So we wanted something neutral. So we started with something new, in a way. What we wanted to is that we reuse the most of what DPDK provides and not reinvent the wheel again on this side of the software. Also, we wanted something easy to use, well, it's more like we don't want to have something hard-coded everywhere. We want something generic and just configure it at runtime, and that's it. Yeah, something modular, because we expect that maybe other people would be interested in this project and that they can go and contribute new code. Yeah, MVP, so just layer 3 forwarding, and with the added difficulty of multiple VRF, meaning that we wanted to be able to handle multiple routing tables. And obviously, we are doing free open source software. So our Grout, so that's for...
Hey.
Over.
This is me. Hello, can you hear me? Okay, seems good. So I'll briefly, or not so briefly, describe how we got from the start to what we have today. And that means the anxious part where we didn't have anything, and then once we got the ball rolling, what was our original design intents and how we got what we have. And I will provide some deeper insight of one Grout module for the IPv4 forwarding, so you can have an idea of what it costs or what it means to implement a new feature. All right. So actually, it's a picture of one of our first brainstorming sessions. It seems it's written "Happy Birthday," but I don't think it's that. Anyway, so we started the project after last year. We seen Jarry and Jacob presentation of the graph library, and it seemed very promising. So we decided, hey, let's try and build a router from that, maybe. And so at first we had the blank page syndrome because I think we were the first external applications using RT graph. So probably we had to weed some stuff that was not completely documented or not explicit in the API. Then we had to ask ourselves, by the way, how do we actually implement a networking stack from scratch? That means reading a lot of standards. And how can we make sure that we will not get into a roadblock at some point because we didn't think about, sure, we need to support VLAN or something else. So one key choice we made is that we wanted to have a strict enforcement of network layers and not try to do Ethernet on IP or do TCP on Ethernet or whatever. So that was a very strong decision we made from the start. And this is an attempt to describe it. So it's just a simplified view of the IPv4 graph, and we arbitrarily cut everything in a very atomic operation. So there's the receive on the layer 1, so on the NIC side, and based on the port ID, we have a list of ports and RX and then we pull packets from that, and we see that these packets come from port number 1, and we know that port number 1 is mapped to a logical interface which is named ETH0 or whatever. And we store that somewhere. And then we go to Ethernet input, which is just removing the Ethernet header. It's not actually removing it, but and then it goes up to IP. And in the IP section input, we say, based on the RX interface we got in the mbuff metadata that we passed along, we can make a route lookup in the correct VRF. And that way, we transported information, but IP doesn't know anything about Ethernet. We could come from an IP interface, for example. And based on the route lookup, we get the next hop if everything is correct. It goes to forwarding, decrements DTL, checksum. And from IP output, we reuse the next hop metadata to determine what is the output interface and some information like Ethernet destination. Ether type is hard-coded because this is IPv4, but the Ethernet output node needs that information because it could get a packet that's coming from IP6 output or, I don't know, MPLS or something else. And then finally, we know that from that interface, we can resolve the port ID and resolve the queue number assigned to that port ID. So this is the simple view. So now we have more global view of, in yellow, it was the previous graph. And we, thanks to our choice of cutting down and say we respect the layers, it was very easy, in fact, to add ARP support or IP tunnel support because we didn't have to add callbacks everywhere or break the IP input function to add something else. It was just adding a new node that does just IP tunnel. And so this is the global graph now. And one of the main benefits of the graph lib is that you have a statistics mechanism in place in the framework. And it gives you for free the number of objects that every node sees, the number of cycles per total cycles spent in that node. And we reuse that to get stack statistics. Like if you get a bad checksum, you will go into the node which is named Rx checksum error, and then you can see that at runtime. And by the way, so that image is generated using a Grout CLI command, so you can just pipe it to graphviz dot something, and it gives you that. So now we have a graph, and we need to have something that will walk the graph in order to process packets. So we have worker threads. You may have one or multiple ones, depending on your configuration. And each thread will need to access non-packet information, like routing tables, the logical interfaces, all these things. And these structures need to be configured. So we have API handlers, which are assigned via lib event. We have a Unix socket. And then we have a well-defined API. So it's not gRPC or something fancy, but at least it does the job. And then so with lib event, we have some background tasks doing the next hop aging, the link status monitoring, and that kind of things. So let's go into more details on one module. So the first thing we need is a set of nodes, which they contain one function which processes the packets. So it gets a vector of packets as input, does stuff, and then it needs to enqueue packets into other nodes. And each node will have a set of known next nodes at compile time. And that means that if you want to have something modular, you cannot, that would mean that the Ethernet input needs to know in advance of IP, IPv6, MPLS, and everything else. And if you want to have something where you have plugins or something that can be loaded at runtime, it will not work. So we added the concept of a modular insertion points. So for example, the Ethernet input node has been written with we check the ether type, and based on that, we have a next node ID, which is registered at runtime. And same thing for IP local, based on the IP protocol. It can go either into ICMP input or TCP, UDP, whatever. It's just registered at runtime, and the IP local node or Ethernet input doesn't know anything about what's next. It just passes the packets along. Also, we need to define in the module that each node, as a contract, will have metadata attached to packets. So the ARP input and IP input will need to know what interface the packet was received on in order to determine the VRF in which to do route lookups or next hop lookups. And same thing for other nodes as well. Then we need to define the set of objects that are being used by the nodes, how to configure them, and finally, so we have a built-in CLI, so we need to implement the commands themselves. Right. So now I will do a short presentation of the project. So a quick overview of the platform setup. We'll start the daemon and then how the CLI behaves. I will do a dynamic resolution of IPv6 addresses between Grout and a traffic generator. And then we'll send some traffic and see what happens. Okay. So give me 1 minute. All right. Does it work? Seems so. Okay. So first of all, let's see. All right. So I have a pretty basic server with 32 huge page, 1 gig huge pages. We have a lot of CPUs, but I've isolated the first 4 are dedicated for Linux housekeeping, IRQs, whatever, daemons and stuff. And all the rest is out of, Linux doesn't use them. And then I have 2 EA10 NICs, which are already bound to VFIO PCI here. And I will use them for Grout. All right. So let's start. So we have a systemd service. Like right now, it's just starting, not configuring anything. I will do that manually right now. But just as a start, we can see that Grout has spawned 1, so the main thread, and then 2 DPDK backend threads. And they are all bound to the first 4 CPUs. So now we can, so there's a CLI like that, and it has, so you can either enter it interactively, which I will do after, and you can also run the commands directly from the shell. And here you have bash completions built in. So for example, I can do X, and then I will create the interfaces. Maybe I should show what's in the file first. All right. So it's just a text file containing commands, and you can pipe it to grcli like this. And so it has created 2 interfaces. Now we can check the running threads. And so Grout has created a new thread, which is a main loop on core 1. So as I said earlier, core 1 is part of the Linux housekeeping, so we don't want data path to run there. So I will remap the RX queues on different cores. And how I will do that is I will type other commands. So here I want to map the queue, port 0, Q0 to CPU2, and port 1, Q0 to CPU22, which are 2 hyperthreads of the same CPU. All right, let's do that. And now we can see that there are 2 main loops now running on 2 isolated CPUs. Okay, and then I will create some IPv6 addresses, assign IPv6 addresses to both of these ports. So grcli. All right. So now we can enter the CLI interactively. So we have the exact same commands, it's just that we have different prompts and you don't have to retype grcli every time. And here, it sort of looks like a standard Cisco/Juniper shell, whatever, something like that. And you can, for example, show IP6 addresses. So we have our link local addresses. And similarly, we have a list of next hops which are known and resolved. But we don't know anything about who's in front. So what I'll do now is that I will go on the traffic generator, and I will initiate a IPv6 neighbor resolution like this. So this is for the first port, and the second one. All right. And now we can see that Grout has learned the neighbor using NDP. And there's a timer. So for now, it's hard-coded. So after, I don't know, 1 day, the next hops are expiring. But it's perfectly OK for a demo. And we can also see that in the statistics, so we received 2 packets, which are ICMP6, and they seem to be valid. There were no errors. We received also unsupported Ethernet packets, which are LLDP or LACP, but we're not supporting that right now. Anyway, so now that we have that, I can start traffic. So I will run at 7 million per port, which is 14 million in total. All right. And now we receive more packets. So let's clear the stats. Right. And thanks to these, so this is all coming from the graph library. And we can see how many cycles in average, how many cycles are we spending on one packet on one node. So that can help with optimizing or seeing where there's a problem or something like that. And you can also check the hardware stats, for example. So I will use that to check if we're missing any packets from the NICs. So it seems not. Everything is fine. All right. So demo is done. Using that feature where you can pipe files into grcli, you can use that at the startup of the service to configure everything. When you do systemctl restart, it configures everything, and then you're good. All right. OK. So let's switch back. OK. So this was the demo. And I will leave the microphone to David.
Yeah, just a few words. So this is a testing tool above all, but still we wanted to see what performance it has so that it makes sense when someone is using it, because if it's only to get 1 million packets per second, it's really not something simulating a DPDK application. So what Robin used is a server quite commonplace, let's say, in our lab, with some interlinks. There's nothing fancy. We did not do any optimization in the code. It's really simple, but just to get an idea, so we compared to test PMD in Mark Forward with some numbers on this system, and we can see that IP forwarding is around 18 million packets per second for 2 threads, so it's quite, it's not too bad. What we can see is that in this piece of software, what is costing the most is IP lookup, since we can see that IPv6 forwarding has an impact. Yep.
The obvious one to compare with is DPDK. No, really, I mean, that's the one people are going to ask for first.
Yeah, but we did not.
We didn't do that yet.
Okay. It will be his job. So yeah, what's cooking? So as you can see, it's a POC. It's getting in a good shape. We achieved what was expected at the start, which is it's a layer 3 router. A bit more features were added, like VLAN sub-interfaces, because it was easy to add, and it proved that it was easy to extend. For the same reason, we added IP in IP tunnels, which was also trivial to add. And so we did some testing on x86 with tune tabs at first for developing, and later with physical NICs. There were some tests on some Arch ARM platform. So yeah, there's nothing really specific with an architecture. It's just working. It's software, so it's working. At the moment, so there is some work on writing a sample module for people to look into it and maybe put their hands in it. Some FRA backend is being worked on so that we could plug, to get FRA pushing BGP into Grout, and testing. So we want to get it with OpenStack people, so yeah, they are looking into it. For the future, so as you can see in the demo, Robin had to pin some thread to some dedicated cores, but in a more complex setup, you may not be able to know beforehand which core you want to map on which RxQ. It may be changing over time during the life of application. So one idea is to work on some automatic rebalancing. So a bit like what OVS does. And otherwise, for the future, we envision adding some more networking features like ECMP, maybe IPsec, some MPLS, and whatever. If you have ideas, we are welcoming you. On the community side, so one interesting thing is that by writing this piece of software, Robin revealed a lot of little things. We had issues in DPDK. So yes, there's a list of the fixes and evolutions that happen in the graph library, in the fib library, and others. You can find the link in the slide if you want to have a look. So Grout has been accepted as an hosted project on dpdk.org. There will be a mail, I guess, to...
I think it just went out.
Okay. So it will be public.
Yeah.
There is a mailing list. There is a GitHub repository if you want to open some issues or some pull requests. So it's a GitHub repo. We also accept contributions via the mailing list. And well, for now, it's for you to play if you are interested, and yeah, all contributions are welcome.
All right.
Questions?
Yeah, there's one question already posted on the Zoom chat, which I suspect other people may have as well. How does this compare to VPP?
Yeah. So for now, we didn't do any benchmarking comparing it to VPP. I am suspecting it's less performant because we didn't optimize anything. But after we did some optimizations, maybe we will do comparisons to have an idea.
Okay, and in terms of sort of design and features and things like that, certainly for me, it looks kind of similar in design and idea. Is that
Yeah.
a fair assessment?
Yes.
On the idea, yes. Maybe there's something different in that we are not copying between VPP descriptors and mbuffs. So on this side, we may have an advantage, let's say.
Yeah.
But after this, they have a lot of optimizations that we don't have. So yeah.
Yeah, so Grout is a DPDK first application, whereas VPP has multiple supported backends, so they need to do some shim layer in order to support RT buffs and other backends. So yeah, it's too early to say if there is any comparison possible. And feature-wise, we're just starting. So obviously, VPP has been there for 15 years. They most certainly support more stuff.
Hey guys, thanks for presentation. Thanks for working on the interesting project. One quick question I have. Do I understand things right that basically the graph is sort of static? So you created at runtime based from configuration file, right? And that's it. You run it forever till you restart your application. You can't add and remove nodes on the fly. You can't kind of change the graph layout. That's what was intended, right?
So,
kind of.
For now, we're reconstructing the graph when we're starting a new worker thread.
Mm-hmm.
So we could change the graph layout at that moment.
Okay,
But
so
we don't do it because we don't need.
okay,
Yeah.
probably I rephrase, but for that, I suppose you need to stop your traffic, you need to state your data plane workers, you can then reconfigure the graph and restart again, right?
So what we do is that we build the graph in advance. When there's a reconfiguration, for example, we build another graph in advance and then we do a hot swap.
Mm-hmm.
So it takes a millisecond to swap to the new graph.
Okay.
Actually, we are not stopping the threads. The threads are just loading the graph.
Yeah, we.
It's just a different graph object. That's all.
Okay.
So we are not stopping traffic.
Okay. Cool. Thank you.
Hey, just going back to the VPP question. Kind of bluntly, why do we need both? Or what's the thought behind, is it just so you can run all this stuff in the DPDK context? Or is it connection to distros? Or?
To answer for that too. So first is we wanted something DPDK first, which VPP is not exactly. We also wanted something vendor neutral. And even if VPP is open source, it is biased towards some VNFs and not others. So we wanted something completely unbiased. That's the main reason. Yeah, sure.
On the FRR integration, are you using the Netlink Linux backend to
The
get?
intention is to use VTYSH, I think.
Oh, that's what it is. You're right. You're right. And any?
Yeah.
So I work on it. Sorry.
So we're trying to reuse the FPM data plane plugin, where you can, instead of configuring the kernel, you can point it to another socket. And as long as your backend understands Netlink, then it's OK. You just need to provide the broadcast and notifications about your interfaces and stuff like that.
So you're listening in DPDK?
Yeah, no. So we'll have, sort of. We'll have because the Grout API is not Netlink, so we'll need some shim layer to transform Netlink into Grout. So either we'll do that, or we'll write a plugin a SO plugin that runs in Zebra.
I'm from Intel, so we've done actually a lot of work in that area over the course of the past year. We should talk.
With pleasure. Cool. Yeah, thanks.